In this next lesson, we're going to look at polarity of molecules. And polarity is very strongly tied to electronegativity. Electronegativity refers to the relative ability of an atom to attract bonding electrons into its valence level. On your periodic table in your data booklet, the electronegativity value for each of the different elements is on the left-hand side, right above the element symbol. And we want to look at the trends that you might see on the periodic table. So if you look up and down or side to side, what you should notice is that there is a general overall trend of those values increasing or decreasing. If you look at metals on the left-hand side and the values of their electronegativities, you should see that the values increase as you go up. So as we go up on the periodic table, overall there is an increase in the electronegativity value. If you look from side to side, from left to right, you should also notice that the electronegativity values increase as we go left to right. A polar bond is an unequal sharing of bonding electrons between two atoms due to a difference in the electronegativity. So if we look at a couple of examples of bonds between elements and look at their values, we should be able to see if there is an equal sharing or not. So carbon and chlorine. Carbon has an electronegativity value of 2.6, and chlorine has an electronegativity value of 3.2. Both relatively high values on the scale. Fluorine has the highest value of 4.0, but there is definitely a difference between those two. Our next pairing, hydrogen and oxygen. Hydrogen has a value of 2.2, and oxygen we see has a value of 3.4. So again, difference in electronegativity, which means that hydrogen and oxygen do form a polar bond, just like carbon and chlorine do. Our next pairing, nitrogen, has a value of 3.0, and fluorine a value of 4.0, the highest value on the table. So again, difference in electronegativity, so this is a polar bond. And carbon, if it's bonded to its same element, then we're going to have exactly the same electronegativity values of 2.6. So this would not be a polar bond because our electronegativity values are exactly the same. A bond dipole or dipole is the charge separation or difference in electronegativity resulting in a more positive atom and a more negative atom within a molecule. So if we look back at our pairs that we did above and pretend that those are part of bigger molecules, we can label the more positive and negative atoms within those. And we're going to use the Greek letter delta to represent our, or to go with our positive and negative signs. So back to our first example of carbon and chlorine, the higher the electronegativity value, the stronger the ability of that atom to attract electrons. So for carbon to have a value of 2.6 and chlorine to be 3.2, the chlorine is stronger or better at attracting electrons. So that's going to be the negative part of the bond. The carbon has a lower value, so it's the positive part. So we're going to label the positive and negatives with the Greek letter delta. Next example, the hydrogen and oxygen. Again, the higher number gets the negative. So our oxygen would be considered delta negative. The hydrogen would be considered the delta positive. Next example, nitrogen and fluorine. Fluorine has the higher number, so it has the delta negative symbol. The nitrogen gets the delta positive. And for our carbon-carbon bond, where they have exactly the same electronegativity, we wouldn't label those with deltas at all. They would just be left blank. Besides just polar bonds, we need to look at the idea of polarity for a molecule in total. So the polarity of a molecule is the result of the sum of all of the bond dipoles. So there's two things we need to consider if we want to determine the polarity of a molecule. First off, does it have bond dipoles? Is there even a difference in the electronegativity of the atoms? Second is the stereochemistry, or the three-dimensional shape that that molecule is making. So let's look at a couple of examples of molecules. We need to draw these with their three-dimensional shapes or their stereochemistry. Our first example, carbon dioxide, you've probably seen a couple of times. So hopefully you remember that it's a linear molecule where you have oxygen on the outside and a carbon in the middle. If you look at the electronegativity values for the carbon and the oxygen, carbon is 2.6 and oxygen is 3.4. So the higher value of the oxygen means that the oxygens are better at attracting electrons. So the oxygens would be labeled as delta negative. They have the higher electronegativity value. The carbon is delta positive. So electrons are being pulled equally and oppositely out towards the oxygens. So if electrons are being pulled both to the left and the right, they're actually not going to move anywhere. So this molecule, because of its symmetry, is nonpolar. Those electrons won't get pulled to one side or the other. It's a tug of war and nobody's winning. Our second example of water has oxygen in the middle and two hydrogen atoms that go out into a V or bent shape. Looking at the values for electronegativity, the oxygen has the higher value of 3.4, so it's labeled as the delta negative. Hydrogen is 2.2, so it's the delta positive in the diagram. So oxygen has a higher electronegativity. This time, our electrons are being pulled in towards the oxygen. But this isn't a symmetrical pull like what we had for the carbon dioxide. So all of our electrons are being pulled toward the oxygen, and those hydrogens are left as positives. Because it's not symmetrical, that means we have an overall shift of our electrons to one side of the molecule, and therefore water is polar. Our last example, methane, CH4, has a carbon in the middle, two hydrogens that are at that sort of odd angle, a hydrogen that's coming out towards you, and a hydrogen that's going back away from you. So this is a tetrahedral shape. Again, comparing the electronegativity values, hydrogen is 2.2, carbon is 2.6, so the carbon is the negative, and each of these hydrogens is a delta positive. So that means electrons are getting pulled in towards the center from all of those hydrogens. This is a symmetric molecule. All of those hydrogens are equally spaced. So if the carbon is pulling equally from all of those hydrogens, no place on the outside of that molecule do we have an area of negative and an area of positive. All of those hydrogens would have the exact same charge. So again, this is a non-polar molecule because on the outside everything is symmetric or the same. Let's look at a few more examples. CH2Br2, two carbons in the middle and two hydrogens. We don't know where those are, so there's actually two possibilities for this molecule. Let's draw the possibility with our two hydrogens attached to the same carbon and our two bromines attached to the same carbon. Trigonal planar shape, and if we look at the electronegativity values, bromine is 3.0, carbon is 2.6, and hydrogen is 2.2. So our bromines with the highest electronegativity value get the delta negative, and our hydrogens get the delta positive. There we go. So overall, are the electrons being pulled to one side or the other? Absolutely. Electrons are getting pulled towards the left-hand side of the molecule. So this is polar. Next example, NH3. Hopefully you remember this is a pyramidal shape. So one hydrogen that's in the plane, one that's sticking out towards you, and one that's going away from you into the plane of the paper. Again, looking at the electronegativity values, nitrogen has a higher value, so it gets delta negative. Each of our hydrogens is a delta positive. So are electrons going to be pulled to one side of the molecule? Yes, definitely towards the nitrogen. So ammonia is polar. C2H4, our next example. 2 carbons and all of our 4 hydrogens on the outside. Carbon is the more electronegative, so it has the delta negative. All of those hydrogens are delta positive. So do we have any asymmetry? That means that electrons are pulled to one side or the other? No, they're getting equally pulled towards the middle. So this is a nonpolar molecule. H2S, next example near the bottom. This forms a bent or V-shaped molecule, just like water does. Sulfur in the middle and hydrogens on the outside. And if you compare their values, sulfur is 2.6, hydrogen is 2.2. So still a slight difference in those electronegativities. Electrons are getting pulled towards the sulfur, and then this is a non-symmetric molecule, so it is polar. N2H4. This one's a little bit tricky to draw, but we want the 2 nitrogens in the middle around a single bond. Then those hydrogens will stick out from the page and back into the page. So on one side, we have our pyramidal shape. Other side, same idea. Typically, this molecule is drawn like this. And this moves those hydrogens as far away from each other as possible. This is very much like the C2H4 molecule. It's symmetric. The hydrogens are the positive part, the nitrogens are the negative part, so all of those electrons are getting drawn into the middle. There's nowhere on the outside where we have more electrons than on another side. So this is nonpolar. And our last example, boron trihydride, this was one of our odd molecules. It doesn't quite fit our pattern. This molecule has boron in the middle and 3 hydrogens that are equally spaced out in a trigonoplanar shape. So, symmetric molecule, boron with a value of 2.2, boron has 2.0, hydrogen has 2.2. Electrons are being equally pulled out towards all of those hydrogens. So this molecule is nonpolar.